Okay, good morning, everybody who's shown up for this year's ROCKE-3D tutorial. We're going to follow the format pretty much as we have in previous years. For those of you that have been here before, we have a few updates to the model that we'll discuss. We recently released the second version of the ROCKE-3D model. But there are not large changes in the model, so don't feel like you have to use the latest and greatest version. The previous versions and the latest versions are not that different, contrary to what you might read in the popular press. Anyway, today we're going to have a few of us presenting, as I can show you here on slide number 2. Myself and Kostas Sigouridis is in the room with me, and Tony Boissetier will also talk a bit this afternoon, and also Igor Alienov, I think, will discuss with us a bit today on our slides. Please mute your microphones at all times for those of you online, unless you need to speak, or raise your hand, and hopefully one of our co-hosts will try to answer your questions. If you have a question that you can put in the chat, that's even better. We can keep things going that way. Okay, so we'll get started, and we'll take a break here in about 45 minutes or less. We'll see how that goes. Okay, and that's tomorrow's schedule. Anyway, I think one of the things that we want to discuss at the very beginning are some limitations of 3D general circulation models that many of you may not be aware of. Some people believe that these 3D GCMs can model things on geologic timescales, and that's very much not the case. They're very computationally expensive models. About the max timescales we've modeled so far are of order 10,000 years or so, and those take many, many months to run on our fastest supercomputers at NASA. The vertical range that the models in the atmosphere itself goes up to about 65 kilometers for Earth-type atmospheres. We cannot simulate escape in this model, and we really only get mixing ratios in the stratosphere and upper stratosphere. We're really limited to shallow atmospheres, as we say here, for the GCM anyway. That means you cannot do mini Neptunes or things like Titan, where the shallow approximation does not work so well. And there are many components to the model, as you can see here on the left, where you see lots of discussions about clouds and the aspects of the ocean and land surface processes. And in the upper left, you can, of course, see how the model breaks itself up into pieces, where we use a latitude-longitude grid system in the atmosphere, ocean, and in the land surface model. This is a picture of the parent Earth climate model. So ROCKE-3D is a branch of the Earth parent model that we produce here at the Goddard Institute for Space Studies. Gavin Schmidt is the lead of that group, and this is a picture from his 2014 paper showing how the model is coupled together with what we call a coupler between the atmosphere, if you run chemistry with the atmosphere that's mentioned here, the ocean component, the land or surface component, which may have a vegetation component if you're using a Earth-type system, sea ice, and even land ice, and then, of course, some shared utilities. So those are sort of the basic underlying features of the model. So I thought we would quickly go through a few of the things that ROCKE-3D is particularly good for. First of all, this is the Planet 1.0 description paper that we wrote back in 2017. Kostas Sigouridis is working on a new version of new description paper for the second version of the model, which will come out in the coming months. But as I said, the second release of the model has gone out just a couple days ago. So if you want to learn about the details of the model, I highly suggest reading this paper. We're one of the few planetary 3D GCM groups that have written such a paper. I think you can learn a lot about GCMs and planetary GCMs by reading this paper. It's fairly high level. We don't go into a lot of details, but what's there, I think, is pretty useful. And it explains to you a lot of the things that you need to understand about the model itself. Now, we've used this model to Model many, many different things. Here you can see Earth 2.9 gigayears to the present from a paper that Tony Del Genio, the former leader of this group, led back in 2018, although we've gone even farther back in time for Earth in recent days. We've looked at things like ancient Venus. This is a paper that I led back in 2016 with many members of the group sitting in this room. We have a picture here of modern ancient Mars without CO2 clouds. Igor Lyenov will talk a bit about this particular version of the model tomorrow. Hypothetical Venus-like world. So we do try to model exoplanets with this model. And in this case, this is a planet in an orbit that gives its insolation close to that of modern-day Venus, but around an M-dwarf host star. This is one of our more highly cited papers in the exoplanet realm on the Proxima Centauri B system. This again was led by Tony Del Genio back in 2019, where we show a series of simulations with lower atmospheric pressures, higher atmospheric pressures, I say here, up to 10 bars of CO2, different types of oceans, different types of ocean salinities, different depths of oceans, all these sorts of things, which is quite useful to understand what kind of capabilities the model has in a scenario like this. Here's a paper that was led by Igor Lyenov on ancient lunar atmosphere. That is a discussion mostly about thin atmospheres, and you can understand the limitations of the model in that respect. But also the Mars papers that we have written. This is a paper that looked at different sorts of obliquities, led by Chris Kalos, one of the members of this group, back in 2019, showing that ROCKE-3D has some kind of hysteresis that we see in basically all 3D GCM models. And of course, spin orbit resonances, which can be done with the model in quite interesting ways, and also geothermal heating, which can be applied to the model itself. So if you're interested in different kinds of geothermal heat from the bottom of the atmosphere, that can be done in this model. And then large parameter sweeps. This is a paper I led back in 2018, showing how if you look at different rotation rates and different installations, what sort of temperate climates or not you can get, and basically looking at the influence of rotation rate and ocean type on what kinds of results you may get out. Typically in this community, a lot of people are using what are called Q-flux oceans on the left. These are slab oceans or thermodynamic oceans, as they're called. That's all described in our 2017 paper. This group tends to run fully coupled dynamic oceans, which are shown on the right. In some regimes, they're very similar. In other regimes, not so similar. Now, why do I tell you about all these papers? I think really the thing that people have found in the past is that the fastest and most reliable way to get a new planet running that you're interested in after you've done this tutorial is to find a similar one from one of our previous papers, so that you don't go essentially outside the bounds of the model. You have to be a little cautious if you go to a new world that is not like something we've modeled before. If you want to do that, I highly recommend you reach out to one of us to discuss it before you produce a bunch of garbage that will never get published. You would not be the first person to do this if you did such a thing, but try not to be the next. So you can find what we call run decks, which we'll discuss a little bit later, but those are basically the configuration files that tell you how to run the model. Boundary condition files, those are things that tell the model how its interior is, the specifics of the model are going to run. So things like topography, bathymetry, atmospheric density, all that sort of stuff, or what we call boundary condition files. And the model output, the summary model output for most of our papers are online at this particular link. So as I said, if you're interested in modeling a certain world, the best thing is to go look at some of our papers, see if we've modeled something similar, and use that as a basis for your own runs. Many groups on the outside have been very successful at doing things in this manner and have produced excellent work with very little minimal input from us. Actually, we're not even co-authors on many of these papers. Okay, so what are some of the caveats So as I've been saying, there are a limited number of atmospheric types that you can run and a limited number of stellar spectra that can run. So if you have a new planet you want to model around a particular M dwarf, you should see if we already have that kind of spectra available. And if not, we should discuss how to create that spectrum for you to use. And if we have time, we'll discuss this in more detail a bit later in the tutorial. Okay, so I would say, what are some of the things that the model should not be used for in general? So I think these are things worth discussing. So right now, we cannot change the mean molecular weight of the atmosphere after the model starts. That means, for example, if your planet starts to get quite warm and you start loading the atmosphere with more and more water vapor, that changes the mean molecular weight of the atmosphere, and things like convection will not be correct because they will assume a given mean molecular weight. This is something we're working on resolving in a future version of the model, but at the moment that will not be possible. And if you're interested in understanding how far you can go outside the bounds, we can discuss that a bit later. Things like super Earths. This is a generic statement about super Earths. I think we're talking more about mini Neptunes, as I discussed before. You can go up to fairly high masses and radii of terrestrial planets, but again, terrestrial planets only. As I say here, where the thin atmosphere approximation is invalid is something you should not do. So things like Titan, where the atmospheric scale height is actually a significant fraction of the radius of the planet. Super thick oceans. Tony Lebois-Citier will talk about this a bit later. This is an ongoing development inside the group where we're looking at doing development for Enceladus type worlds or Europa type worlds, but that's not quite ready for prime time. So that's why we say you probably should not be used for that, because again, the thin atmosphere, or in this case, the thin ocean approximation, is what we're dealing with. And if you're looking at modeling an ocean like Europa or Enceladus, the thin approximation will not apply. And as I say here, not above temperatures of 400K. What do I mean by that? Meaning that if a given grid cell reaches temperatures above 400K, you're probably outside the bounds in general of what the model is capable of doing on the radiative transfer side. And what you will find often is the model will bomb, or it will start sending a lot of messages to one of the log files that you should keep an eye on, telling you that you're outside the bounds of the model. And I say here, not below about 100K, except there are a few exceptions to that. There's Titan and also some of Igor Alienov's moon simulations, but in general, for most of the radiative transfer files that we provide, you really cannot go outside these bounds. Another thing that the model is not good at is for really cold planets. If you're using a fully coupled dynamic ocean, the model is not good, is not happy when the ocean freezes to the bottom. As one of our colleagues, Max Kelly, has said, the ocean doesn't like being squeezed out of existence. And we do not, unfortunately, have the capability at the moment to change surface types dynamically. So in a case like that, in theory, the ocean should change from, if it freezes at the bottom, it should change the surface type to a land ice, but that's not capable at the moment, so the model freezes. So if you think your model is going to be very cold, be very cautious about using a fully coupled dynamic ocean in a case like that. The slab oceans are much more forgiving in that respect. Fast spinning planets. So I say here grid resolution. So planets with rotation rates that are faster than about 12-hour Earth equivalent don't really sample the Rossby radius of deformation very well. So if you are going to do grid resolutions like that with the default 4x5 degree model, you probably want to consult us about whether that's appropriate or not. I've already mentioned mini Neptunes, gas giants, etc. These are not really appropriate for this model. And I would say, remember these terrible acronym we have for this model. Resolving orbital and climate keys of Earth and extraterrestrial environments. This is basically stuck to terrestrial planets. Let me just hide this. Yes. There is a South Pole anomaly, as we like to call it. We like to provide funny names for things that are simply explained, that we cannot get rid of the South Pole in the model for various reasons that we will not have time to go into the model. But the South Pole point is a very, very small point. In the Earth climate model, it's not an issue because they have Antarctica and they don't care. But for those of us that are interested in modeling, for example, aquaplanets, you have to consider that you have this funny South Pole point down there. And there are, of course, limitations in atmospheric constituents. You cannot just model whatever kind of atmosphere you want. For example, if you wanted to model a 10-bar methane atmosphere, we cannot do that with the current version of the model. We cannot model 10-bar H2 atmospheres. It's very dependent upon the radiative transfer, and we'll hear about that tomorrow from Eric Wolf. Okay. So if you have some problems with the model, this is a list of everybody in the group, or most of the people in the group, that are experts in various aspects of the model, or if they're not an expert, they will know who to ask. At the top, I should mention that Andy Ackerman, our cloud expert, has recently retired, but he's still around, and hopefully he'll still be able to answer questions. I'm not going to go through all these, but you'll meet many of these people over the next few days. For chemistry, aerosols, that's Kostas and I say here Kostas and Sunny for chemistry. Sunny Harmon's one of the members of the group. He's a civil servant at NASA Ames these days. For radiative transfer, that would be Eric Wolf. On the Socrates side, which we'll talk about what the difference between Socrates and the Gibbs radiation scheme are tomorrow. Atmospheric composition, debugging, calendar, we'll talk about tomorrow. Tom Clooney could not make the tutorial this year, but I will talk a little bit about that. We have some land planet capabilities in the model, or I say here biology. This is probably a very broad term for something that's very narrow. You can talk to Nancy Kang about that. The land surface model, Igor is our expert. Oceans and sea ice, that's Tony Leboisite, which talk about that a bit later today. And Panoply is a tool that's built in-house to look at the post-processed data from this model. Basically can read what are called netcdf files and tell you the state of the model and various other things that you might be interested in, like the surface temperature of the model. Okay, from here on, I'm going to let Kostas take over and discuss some of the slides. Do you want to chat from there and me forward, or do you want to come over here?
Tell you click.
Yeah, sure.
So, okay, so we'll go into the weeds here. And first of all, something that we have already seen from the emails we've sent out, that the Simplex website and the ROCKE-3D website, and we have some documentation there. And the important thing is that we have the snapshots, that they are being updated. Some of them are being updated, some of them are frozen, and it is the place to go to download the model. Next. And so this is the top half of the figure here is the snapshot of. It's essentially a screen capture of how the snapshot website looks like. And you can download the Planet 1 and Planet 2 models that you can see at the top. 1.1 is just includes some updates that are not changing the model's answer. So you can there are some options to enable fixes and bugs that we found and that will change the answer. But if you download it 1.1 or 1.0, it's practically similar. We have an under development branch that is keep going, and that's a moving target. You download it at your own risk, and you can see that there is a date in there. That doesn't necessarily mean that it is the date that the last time the model was updated, but it is the date that this file was last time generated. And I'm not going to, there is some internal reason why we do that like this, but it's, you don't care about it. The important thing, Planet 1.0, Planet 2.0, you can download them from there. And we'll be discussing here the differences between the 1 and 2 in terms of configuration. They are very, very new. So we have a lot of no-model versions, and we try to put them, to sort them out by having version numbers in the most recent years and try to be more careful about that because people were confused. So we have this model E2 that was used for CIMIC 5, and it was the basis of Planet 1.0. Then we have Planet E2.1, which was used in CIMIP 6, and it is largely the basis of Planet 2.0. And it says there in the slide, Tracer C3, that's an internal lingo, don't worry about that. And we are working essentially in Planet 3 that will include many changes in the cloud physics as inherited by model E3, and but this is not ready yet. It will not be ready for like not soon. And the planet branch, the planet that we have there without the version number, that's our moving target, the development branch that is mostly seen internally. And you will probably not be seeing much other than the frozen versions. Then we have three ways to calculate atmospheric composition. One is called NIMT, and it's highlighted in red because this is the one we'll be discussing here. So you prescribe the atmospheric composition like greenhouse gases and also the main constituents like nitrogen, oxygen, or whatever you have there, and that's fixed. But in case of O-MINE matrix, these are versions that contain gas phase chemistry, but also aerosols, and they can calculate prognostically the atmospheric composition of the atmosphere for the trace gases and the aerosols, not for the carrier gases. So oxygen will, for the case of Earth, will still remain fixed, but for other things that are in trace amounts, like methane, for example, it can be calculated prognostically. We will not be discussing about that because there are some limitations for the ROCKE-3D. The important thing is that with our current chemistry, you do not have the capability of running an anoxic atmosphere. So there must be some oxygen available. Next. So I hope you've downloaded the model in your, as was recommended in the emails we've sent out. And so there are some important things that you need to be doing for setting up your model environment. One is setting up your .model ERC file, which contains everything about your environment, essentially, where the directories are, input files, where the output will be stored, where the compilers are, which ones to use, things like these. Then we have the main ROCKE-3D home directory, which is listed there in the second bullet. As an example, it can be anything you like. You decide how to name this, something that makes sense to you, and you can even have multiple of those if you want to do different types of works that you don't want them overlapping. And then within that home directory, we have the templates, the decks, and the model. These are not the only subdirectories, but these are the key ones. So the templates contains the blueprints, essentially, of what we call the run deck, which contains all the information about the model configuration. Then you cannot use the templates directly. You have to create a run deck from a template. So when you create a run deck from a template, it is saved in the decks directory that is listed below. And we'll go through that in more detail later. And the source code of the model, which is practically all of it Fortran, is in the model directory in some subdirectories. As defined in your .model ERC file, which lives in your home directory, there is a place called GCM search path that contains all the input files. You can change it to whatever you like in the rundex, and then in the rundex, the input file is defined. We'll assume that everything is in that directory or subdirectories of that, unless you define something with a slash. We'll also show examples. And you can define your own input files. You can create as needed, if needed even. And you can put them anywhere you want in your file system, as long as it is available in the computing environment. If you put them in the GCM search path, then you don't need to provide the full path of it, just a relative path from there. But if you put it anywhere, like in your home directory, it has to start from a slash. And the output files are saved in the save disk variable in .model ERC. and they are soft linked in the DEX directory.
I would just like to add that the save disk is where your model output, as Costa said, is going to end up, and that can be gigabytes of data. So consider that where you're saving your data. You might not want to save it to your home directory because you might have a very small quota. That's how it works on our supercomputing system. So most of the model output is saved to a different file system, and that's the advantage of using this .model ERC with these different sort of shortcuts, as you can define it wherever you like. We'll talk about that more later.
So, what is this rundeck that you create from it? Essentially, it has a name that is called, it's the run ID of the simulation you're going to run, and the suffix of .r, uppercase R. And when you open it, it contains hundreds of lines probably, and but they are all of them listed. Can be categorized in those bullet points that you can see. The very top of it is the documentation. You can write anything you like. Then that describes your run. Then it is a section that is called the preprocessor options, which says which large blocks of code should be enabled into the configuration we're setting up. Then it is an object modules small thing, which is essentially says which modules to compile. And then it also contains the files to be compiled if they are not in standalone modules. It sounds kind of cryptic, but we will see a rundeck and you will see that it is not that bad. You just list the files essentially that the model needs to be aware of to use for compilation. Then we have the components and the components options, which are the additional files to be compiled that live in subdirectories of the model code. And then in that case, you do not have to list them one by one. You just need to list the components and that's it. And then every component has its own makefile. Then there is a long part of the rundeck, maybe half of the rundeck is that, the data input files, which is essentially everything that the model needs to know where to read in. So emissions, boundary conditions, radiation tables, anything that is an input file. There is a read statement in the model. You need to say where this file is into this data input files section. Then there is a single line in the rundeck that contains the label and the name list of the run. Essentially, it is saying the run ID and some comment that you want to show up in your output files. And then the second biggest part of the rundeck, or maybe even the first one, it's the other half of it essentially, the parameters section, where you define how the model will behave outside compilation and input files. So there are several, think of it as this. There is a variable in your Fortran code, and you want to control it from outside the model code. So instead of recompiling all the time, you might want to change this parameter through an external means, and this is the external means. So you decide, let's say if there is a lifetime, the time step of the model, you can set it up from there, and you don't have to recompile the model every time. It's maybe the lifetime is not the best example because you don't change it that often, if at all. But it is essentially a way to control how your code behaves and you can stop the model, pause it, change something, continue. It's this is where you will spend most of your time actually. And then at the very end, there are 3 lines that they start with input Z, and they essentially say to the model how long it will run and for which years. So it has a start time and then end time. And these are usually nominal numbers. So it can be anything like 1 for start time, start year, and 1000 for end year, that will run for a millennium. And it also contains some things about how to start the model exactly for how long, but essentially it just says to the model for how long it will run. For transient simulations, there is a way to say that, simulate the year 2000 up to the year 2020 if you are simulating Earth. But for planetary applications, we don't really do that because there is no real year. And but we will go into the rundeck, and at some point I will mention that. But for the most common simulations, start and end years will be nominal, but they are the ones that will show up in your output files. So you need to know.
Question, Kate?
Yes.
What is the difference between the nameless and the runtime?
The name list is the label is what your run ID is, and then essentially you can write anything you like. That's the name of your run. The parameters are configuration options for the actual code. So,
if I may add,
yeah.
actually, this label and name list is a little confusing statement. So basically, you can put anything you want in this line. It just originally we had name list and label there. It's basically just something that will be printed out, but it's only for diagnostic purposes. It doesn't have effect on real computations. And if you are talking about name list and parameters and inputs, those are basically the same thing. It's parameters and then inputs parameters for timing of the model, but inputs are basically inputs use exactly Fortran name list format, while parameters use our own in-house format. So please don't confuse those. Basically all this happened for historical purposes, and we still keep them. So yeah, so this label is just a label and nothing else. And everything else. And I wanted also to say that please assume this format as something like in-house. Don't write something unusual with it. Don't assume that it's written in certain known language. It's just the way it's written. It's how it should be used.
Okay, move on. Any other questions in the room? If you have questions online while we're going through, please ask, because this is the time.
I am also monitoring the chat.
Okay, plus it's also monitoring the chat, so please don't be shy. Okay, we move on.
Okay. So I said that you create Randex from the templates, and for the case of Planet 1.0, we have those 4 Randex that you can see there. And P stands for planetary, 4 and 1, ignore it. Then S, uppercase S, stands for Socrates radiation. M40 means the medium resolution, so 4 by 5 degrees in latitude and longitude, and 40 layers. And then if there is an O in the Randex name, as in the 3rd bullet, it means that there is a dynamic ocean. If there is a Q, it means it is a Q-flux ocean. And if there is nothing, it means that the ocean is prescribed or there is no ocean. And the 4th bullet there is the template for Mars. It is not literally Mars. It is our first attempt to simulate Mars. So you can consider it as a generic Randex for a desert path with no ocean. So there are many more templates. Many of them, if not all of them, are for Earth configurations. Some of them are abandoned. So please don't just pick one because you think it sounds what you want and use it. Let us know if this is the right one to use. And then in moving into the future, if you are using this model for your group, for example, there are many users, and there is one particular planet that you are all simulating, then you can create a template for your group and put it into the templates directory, and then you will have something that you can use in the future. For Planet 2.0, there are many more Randex options, and I will go through them in a slide later. And but as I mentioned earlier, don't confuse the template with a working Randex. The template might work out of the box or not. For Planet 2.0, it will not. So you must create the Randex from the template to the command that we have already sent you. Okay.
I just want to say that in most cases it will not work because template actually is not a Randex. It's contains certain instructions how to process it. It's contains CPP instructions, so basically it has to be run through script to create a function Randex.
Good point.
So for planet 2.0, the pattern of the name is highlighted there with those colors. So P2 stands for planet 2, and then there is an option to choose either G or S, which is the GIS or the Socrates radiation. And then there is an option to choose the atmosphere, which means A is for the atmosphere of pre-industrial Earth. X is same as A, but without aerosols, without ozone, and without stratospheric water formation from methane oxidation. It is essentially a backward compatibility with planet 1.0, but you should not really be using that moving forward unless you want to compare with planet 1.0, because that atmosphere has oxygen as one of the constituents of the atmosphere, but it does not have ozone, which is probably inconsistent. Instead, you should be using the atmosphere with an uppercase N, which means anoxic, and it is the same as X, but with no oxygen and argon. Everything is 100% nitrogen and plus trace gases. Then with the black, you see the choices for ocean. P stands for prescribed sea surface temperature and sea ice. And the Q stands for Q-flux. This is a 100-meter mixed layer depth, which is deeper than the planet 1.0 that we had. And O is the dynamic ocean. Depending on resolution of the atmosphere, the dynamic ocean follows. And so the resolution of the atmosphere is either F or M. M is the same as planet 2.0, 4x5. You can use it for fast simulations or for smaller sized planets. F is the fine resolution, and you will need it for bigger sized planets. And so you can think of a ballpark that for an Earth-sized planet with an F resolution and the Mars-sized planet with an M resolution, the grid box in terms of kilometers is about this. So when we are using the medium resolution atmosphere, the ocean has a 4x5 resolution and 13 layers. When you are using the fine resolution of the atmosphere, which is 2x2.5, the ocean has a 1x1.25 resolution with 40 layers. It might sound too much, but it really isn't. It's pretty straightforward. All of those Randex exist. All of those templates exist, and you can do mix and match. We have vetted them. They work as expected.
Yeah, and I think I also want to add something that's a bit important about thinking the kind of science that you're doing determines what kind of run deck that you choose. I know that most people think higher resolution is always better, and that may be true. But in this case, if you, for example, use the F40 model, it might run 4 times slower or even more slowly than the M resolution. So you need to think about your science case when you pick the resolution of your model. If you're thinking about simulating Proxima Centauri B, you probably don't need the F40 model because you don't need this kind of resolution to get a climatology for such a planet, because we're never going to have F40 resolution. We're never going to have the M40 resolution, not in our lifetimes anyway. So think about the kind of science you do before you choose the resolution. I would say so far, all the outside groups that have used ROCKE-3D have all used the M40 resolution version of the model because their science sort of dictated that. But for example, if you wanted to do paleo Earth simulations and you had sufficiently high resolution boundary condition files, which is not a given, you might want to use the F40 resolution in a case like that. But otherwise, think about the kind of science you do when you pick the run deck that you want to use. As Kostas has gone through, you need to think about what kind of atmosphere you want to have, and that will determine the kind of run deck. You want to think of what kind of ocean you want to have. That will also determine the kind of run deck. What kind of science do you want to get out of using this model? That's the first priority here before you decide what run deck you want to use. And I would just say, I know this looks very confusing from the first time you see it, what we have described here, and it is. So if you're unsure what to use, ask us, and we will help guide you to some degree. I think this is really important for those of you that are using the model for the first time, or if you don't have someone else to consult who's very familiar with these type of models. it's really critical to talk to someone, at least at the beginning of your project, to decide what's appropriate for you to use.
And do not underestimate the computational cost of adding the dynamic ocean or the fine resolution of the atmosphere. And also do not underestimate the amount of output. It's 4 times more output, actually more than 4 times more output if you have the ocean, if you are using the F over the M atmosphere. And you just need to budget for that. And so the workhorse simulation for this Planet 2.0 is going to be the P2 model, obviously Planet 2, with Socrates radiation, with the N atmosphere, the dynamic ocean, and either the fine or the coarse resolution, whichever you like. But the acronym should be P2SNO and then FOM. You can figure out.
Right. And I would just want to add one other small thing. Most of the other planetary GCMs are not using or not capable of using fully coupled dynamic ocean. So the O in the ocean section here. If you want to replicate someone else's work from another group that has used a different GCM, most likely they're using what we call in-house a Q-flux ocean. That's the Q simulation. So you can reproduce or try to reproduce other people's work by using that particular type of ocean. And as Kostas said, those are less computationally expensive than using the fully coupled ocean, which is why most other planetary groups use these types of oceans, because they are computationally efficient. You can get a climatology with a Q-flux type ocean in a week or two with most models. You will not get a climatology in equilibrium, at least, with a fully coupled ocean in that kind of time scale. It's very difficult, depending on what kind of boundary conditions you set up.
And speaking about the Q-flux ocean, I just remembered that other than the depth difference between Planet 1 and Planet 2, in the 1.0 version, we had the Q-flux of present-day Earth. In the Planet 2 model, we have Q-flux 0, which is probably not realistic, but this is the community standard. So we decided that we should go with that as a easy benchmark for other simulations.
Yeah, just to touch a little bit on that. So what Kostas is saying is that when we say Q flux is equal to 0, means that there is no defined heat fluxes between the grid cells and the ocean. And that's what the exoplanet community in general does. They don't know what they should be, so they use this. These types of oceans were developed in the Earth climate community when they did know what the fluxes were from, for example, satellite observations or fully coupled simulations, and they could set the fluxes and the model would run much faster. So in the Planet 1.0 version, Kostas right, we set this to Earth values for Earth simulations. You wouldn't want to use a Q flux with a given value for a non-Earth simulation. But another thing is that this Q flux ocean depth can be made smaller or larger. It depends again upon what kind of science you use. We use 100 meters. Probably most groups are using 50 or less. It may depend upon what kind of science you want to get out, what kind of depth you want to use. But computationally will make very little difference. So maybe we take a quick break here, like we have planned in our schedule. And I'll pause the recording, but if you have any questions that you want to ask, please put them in the chat.
Maybe we can go to the next slide.
Yeah, well,
No, okay.
let's just take a break, then we keep going. So we will. Okay, Kostas, why don't you take it away?
Okay, so we will do a little bit, go deeper into the weeds actually, and see the actual Randex. So what we will do in a minute is that there is this one Randex P1SOM40, which is for Planet 1, Socrates radiation with dynamic ocean M40 resolution, and then compare that with, for example, P4, forget about the number, what the number means, SQM40. So essentially compare a Randex with the dynamic ocean versus a Randex with a Q-flux ocean. And then we can even compare the dynamic ocean run deck with one from Mars, which is it's going to be very, very different. And of course, as you can imagine, far simpler. So there is this website here that has a complete list of variables that are available in the model. It's a very, very long list. And in practice, you can find all this information from this website by just grabbing the code if you know exactly what to grab. Because this website is generated by the actual model code. And so anyway, yeah, let's go next. So we'll start from the bottom. I mentioned that at the very end of the run deck, there are the start and stop times, and there are these three lines here. And as an example, you see that the first line says when the model will start. So it says start on the year 1897, and the first month will be 1, the first day will be 1, and the first hour will be 0. So it will be exactly at the new year, when the new year comes in for the 1897 year. The model will stop at the year 1910, month 1, date 1, hour 0. So the moment the year 1909 ends, the model stops. And I'll skip the next line with the I start and go to the following one. We say master year equals 1850. This is in the parameters of the file, of the run deck. And this is a key thing that says which actual year to simulate. So here we say year I 1897, year E 1910, but since master year is set to 1850, it means that for all those 13 years of the simulation, the 1850 will be repeated every year. And the numbers of the years in the output files are just indices, just a way to show the increment of the years. So you will be getting a climatology, a 13-year climatology essentially of 1850. Now moving to the line that says I start equals 2, the number 2 means that this is a cold restart, as we call it. Probably the correct way to say it is a cold start, not a restart. So essentially the model starts on whatever initial conditions you provide to it. And then if you see the year E, etc., later it says 1897, month 1, day 1, hour 1. So it is only 1 hour later after the year I line. And this is what we call the setup hour. And what happens is that you need to do a setup hour always when you start a new model simulation. And the setup hour reads the initial conditions that you provided, whichever they are. And then it runs the first 2 time steps and saves a restart file from which it continues running as it goes until it hits year E, so when the model stops. So in practice, you run the setup hour, the model stops, and then you say to the model, okay, now continue running. Sounds funny, but it makes sense, really. So yeah, what's the next slide? Yeah, okay, so okay, let's do that as well. So we mentioned the 4 different run decks earlier. I have them there just to see them. And below are the commands that we have sent you to see what you need to be doing. And for creating your first run deck from a template and working with it. So let me share my terminal. Is that big enough?
Get big.
Okay, so you can see here the Planet 1 templates that I have. And you can take, let's say this one, P1, I said SO140, right?
Yeah.
So P1 SO140, and we can, so in my Dex directory, there is only a make file. So we can do a make run deck run equals this, run src.
That's the template you're
So
giving.
this is the name that you want from the templates. And then you say run equals, which is the name you wanted here. And let's say this will be this one, TUT from tutorial. And that's it. And the model, and then the run deck now is generated for you. And this is the one that you will be using for run.
Yeah, that run is the run ID. He's giving it the run ID,
Exactly.
P1SOM40TUT. And again, the template is what the run source is equal to, P1SOM40. Keep those separate, as we've said several times now.
And then the next one that we want is the Q flux, and that starts with a 4. So the Q and the 4. Same command essentially, and we create a new template, which is here. And then we can compare those two run decks. And you see the differences here. On the left, you have the dynamic ocean. On the right, you have the Q flux ocean. So there are differences in the comments section, ignore those. You see that we define the ocean, and then there are some other differences in the input files. I'll go into one of the two, not the comparison. There are some differences in the, sorry, these are differences in the source files. Further down, there are differences in the input files. Even further down, there are differences in the parameters section. And then that's it. Very few differences. So let's go see one of those. And I will take the simpler one, the Q flux ocean. It doesn't matter which one. And we start from the beginning. So remember the order that I told you that it exists in the randoms, right? So the top part of it is comments. You can write anything you want. And document your run deck, say when you started it, just anything that will remind you what this run deck is a year from now. Then we have the section that starts with preprocessor options and ends at the end preprocessor options. This is the large scale control of what things you need into the model. So importantly, we say we use the planet params, not Earth. So this means that this is something like Earth, but not really Earth. So, but most of the planet parameters will be Earth, but in a more generalized sense. We use the planet radiation, meaning Socrates, and we turn off the GIS radiation. And then we have where it starts with object modules and continues for quite a bit up to here. So just before the word component. So all this section here is saying which Fortran source files to be used for compilation. And you do not put the extension to them. So when you see model E, it means there is a file that is called model.f or model.f90. And it will use it when the model compiles. And then after this section ends, the components section starts, which says which components to load. So these need to be subdirectories into the model code. So if there is a file that is called ocean.f in the model directory, there is also a directory called Socrates into the model directory. And for those components, they might or might not have an option. So when you see something that says OPTS_end, it means that for the end component, the options to use are these. You will most likely never touch those things, so don't worry about it. Then a key part of the run that comes in, which is a data input file. And in here is where you saw, you list everything that there is an open file command essentially in the Fortran code. And if you remember, I mentioned the GCM search path, which is in your .model ARC, which is where you define your input files, the directory of your input files. So if it is in there, you don't have to say anything more. So for the AIC input file, whatever that is, the file name to be used is this one. And it automatically means that this file exists in the GCM search path directory. You can use a relative path, so if it is in a subdirectory, you can list it here. But if it is outside the GCM search path, you have to list the full path, so /home/users or whatever. So from these input files, there are some really important ones. Do we go through those later or
Maybe,
now?
yeah, why don't you mention a few of the,
Okay, so just selectively a few things. The AIC file is the file that will be used for the initial conditions of the atmosphere, atmospheric initial conditions. GIC is for ground initial conditions. And if you're running with a dynamic ocean, there is an OIC area. This file is used for I start equals 2, so the model starts from cold start. But if you want to continue a simulation that you have done in the past, you can start from a restart file of that simulation. And in that case, you list that restart file here, and you change the I start value. Then there are other things here, like the vegetation cover, what it is, the crops, if there are any, radiation input files, radon 1, radon 3, etc.
those
You
want
don't
to
need to
change?
know those. Yeah. You don't, so, and then GHG, this is a really important file. This holds the concentrations of the greenhouse gases that are in trace amounts in the atmosphere, like CO2, for example, or methane on Earth. And this is where the model will go look into the values to use depending on the year. So I mentioned in the last slide, you've seen that master year equals 1850. So that will tell the model, go into the GHG file and tell me what the concentration of the greenhouse gases were in the year 1850 and use those. So in a planetary sense, since you have to make a choice of the master year, we don't really touch it. We just go into the greenhouse gases file. We use a file that contains our information. We set a line that says 1850. I think we also say 1849 and 1851. Set the concentration there, and that's it. I mean, this is nominal year. If you simulate Proxima Centauri B planets, there is no year. So you just set the value there that you want, and that's it. And you use that number.
Do you want to show
If-
GHG file?
Yes. If the number is outside the range that we have defined in the years, it will pick the closest one. So if you have 1850 and your master year is 2000 or 3700, whatever, it doesn't matter. It will pick the closest one. So let's see what this file looks like, because this is a really important file that you will be changing. So this is how it looks. It's just an ASCII file. It has, you need to have it exactly as you see it. So don't change the indentation. It needs to be exactly that. Because it's a Fortran read file with some format, so you need to be careful. So this file starts from 1850 and lists the concentrations of CO2, N2O, methane, and 3 types of CFCs. Others here are other CFCs. If something is 0, set it to 0. As simple as that, and then it keeps going down up to 2008 for this package. Going back to the render, so you can create your own greenhouse gas file and set it populated with the very.
Just wanted to mention that at least in some versions of our model, the model assumes that there are at least 2 lines in there.
Yeah, I said that, yeah. But you need to define the 49 and 51 here.
Yes, something like that, because in theory, one couldn't spell just 1 line, but some versions of the model will not understand that.
And also, maybe you could show the planograms file for not Earth.
Yes.
Go back up.
So Mike is speaking about this one. So when you create, we will discuss in detail about that when we are creating a new planet, but we can see what that looks like right now. So if you go to the model directory, and then this is in
Shared.
shared. So
Yeah, whatever.
So we have a number of planetary parameter files here, and it's this one, right?
It's no, yeah, that's right.
So in this file, this is the Fortran file that contains the module planet params. And in here, it defines things like the gravitational acceleration, the planet radius, the molecular weight of air, of the atmosphere, the partial pressure of nitrogen, and some really core things that the model is having. And then the values used depends on which case we have. So in the not Earth planet params definition that this run that you are looking at has, these are the values we're using. So the name is not Earth of the planet, the acceleration of gravity, the radius, etc. And then if you go further down, this is the like Mars that I told you it is not exactly Mars, but close. And it has different values here. And then we have Proxima Centauri B, and that's it in this one file. But this is where you will be creating your own planets. And you will be listing things here. And everything you see here is constant. It cannot change. And this is essentially what Mike was saying. The molecular weight of air cannot be modified at random. So back to the RAM deck. So these were the input files. And then we have the section here that says parameters and continues all the way to nearly the end of the RAM deck. And in here are the things that you can change at will in general, but not all of them. So it lists things that essentially when you change them, you don't have to recompile the model. And it says what type of ocean to use. It says computed because this is a Q-flux ocean simulation. It says like this, which solar spectrum to use. It says the sun. It lists you further down the solar spectral files. It lists you some tuning parameters that
You should never touch.
Yeah, don't touch them. This can largely mess up a lot of things. But if you're creating a new planet, we can chat about that. This variable here says use uniform greenhouse gas concentrations instead of having a profile or some latitudinal gradient. O3x is a number that you need to multiply the default ozone concentration. So multiply by 0 means take it out. CO2x says multiply by 1, which means take the value you found in the greenhouse gas file and multiply it by this one. So it's a different way to control the concentration. So think of it like this. If you want to study a range of CO2 concentrations on a planet, you create one greenhouse gas file for that planet. You set the default CO2 concentration in there, and then you use the multiplier for different sensitivities. The alternative would be to create multiple files and change the file name of the greenhouse gases and don't touch this one. There are some limitations in older model versions on exactly how this works with vegetation, I think, but this is solved now, right? I think so.
No, I think everything is fine unless you're using some funny parameters that you probably shouldn't describe. Yeah, okay, just all that. So everything should work.
So further down, you see master year that is a really key parameter that is you are probably never going to change it, but you really need to know what this really means. And then more things here. These are time steps for the model, and these are some filters that are using lots of time steps. Yeah, I really don't want to go through those one by one. This end disk value is important. The model, every end disk number of time steps, for 8 in this example, is saving a temporary restart file on disk. So if something goes wrong and the model crashes, you don't have to go all the way back to the beginning of your simulation. you have a cushion and you can start from there. For example, your computer crashes, or some administrator reboots it, and while your model is running, I mean, these things really happen. And so the model has two files that it is saving, the fort.1nc and fort.2nc, and it says once one, once the other. And this is for safety reasons, so that if something happens while saving this file, then the file will be corrupt, but at least you have the other one. So
480 disk
yeah,
and just time steps before. Yeah.
exactly, yeah. So the model time step is 30 minutes. So 480 is quite frequent. And it really is, if you do that really frequently, it will very, very visibly slow you down. And I mean, you can easily increase the simulation time by a factor of 10 if you set n disk equals to 1, for example. Which you might need to do it for certain debugging things, but in general, even 1,000 or 2,000 is safe enough, but it depends on how stable your model is and how comfortable you are with that. It does not modify results, but it's an important number that you need to keep an eye on.
I mean, and the other example is, let's say on your supercomputer, you're running 40 models at the same time, and you're using the same file system. You have to consider the disk I/O on the computer. So you do not want to have this be a very small number. Otherwise, they're all going to try to write at very similar times, and your model's going to be slow, not because of computation, but because of input output. So there are some advantages to making this number a factor of 10, or in some cases, maybe even a factor of 100 larger than the default value.
We have a few useful commands like QRSF, which allows you to see the exact date of your folder 1 or folder 2. I think in the
Well, that's internal command which you can see on if you are working on Discover. Otherwise, normal. But it depends on the architecture you are running on. So if you are running on your laptop, which has extremely fast solid state drive, you probably shouldn't run it too much because your model will be slower in general. So maybe you want to save your restarts faster, more often.
So the way to decide is this: how much simulation time you afford to lose if something goes wrong. If your model is super fast and it can run a full year in like 3 hours, then for whatever reason, then you don't need NDisk to be something small because it's really quick. And but if it is a super slow model and it takes a week to run a simulation year, then you really need to use NDisk something small, because if something goes wrong, then the time steps move slowly. Another important variable is k-copy equals 1. Don't touch this, otherwise you will not get output. And another important one is the KRSF, which equals to 120 here. RSF is the restart file. That's what the RSF means. And KRSF means every how many months to save a restart file. And I mentioned 4.1 and 2 as restart files, but the RSF file is a more formal restart file. It is the one that you will actually be using for most cases to continue simulation or to make perturbation experiments or something. And they are not being overwritten by as the model goes. With the 4.1 and 2, they alternate. The RSF files persist, and they contain a date, and they are really big. They will dry out your disk space if you set that to 1, and they will also slow down your model simulation. There are cases that you might want to save them for every month, but don't do that for long simulations. This 120 says every 10 years, meaning every 10 orbits, and we will go into the calendar tomorrow. But in general, think of it like, yeah, it's if you don't care at all about restart files for whatever reason, you will never use them and you are happy with the 4.1 and 2 only, you can set that to 0 and it will never save anything. These are really big files. It saves, they contain the full model state in 3D in double precision. It's really, really big file.
So just checking, a month is defined as the 12th of the orbital year. period.
A month is the 12th of the orbital year, but it might not have the number of days you are used to on it. Yes,
We'll
we'll get
discuss
that,
that
we'll
tomorrow.
go into details tomorrow. I think the only, when we go to a different planet, the single number that stays the same with that on Earth is that a year, that an orbit is split into 12 months. That's the only thing that stays constant. Everything else changes.
Well, also, every day has 24 hours.
But the hour is not necessarily.
Hour make a different number of seconds.
Yeah, but so it's not the same.
It's confusing.
Yeah.
Yeah, we call it an hour, but it's not 3,600 seconds.
Yes, the second stays the same, and basically the orbit stays the same. Everything else is just.
And I guess we still call an orbit a year. No, we don't.
We'll discuss this tomorrow.
Yeah, we'll discuss it tomorrow. It's complicated. That's why we have a separate spot for it. Should I say anything else for the run deck?
We want to mention NI surf.
Did we ever change it? Can you say that? Or you're better to explain that.
Well, I can explain it later.
I mean, NI surf essentially is how many times you run the surface processes in every physics time step. And but yeah, I think we know more than that.
Yeah, sometimes you need to make it a bigger number, depending on what kind of physics you're dealing with. Well, maybe
But it can't be any number.
Huh?
Right, usually it's,
Well,
it should be, I think, even number.
yes, exactly.
I mean, either one or even.
Yes, one or even. Yes,
Yeah.
don't just pick 5,000.
Oh, 5,000 is even.
Well, there's a reason not to
But don't
pick
pick that.
5,000.
Don't pick that, yeah, it's too often.
What else?
I-
Maybe, I guess Chris will talk about the planet params, because that's where also you can set things like if you want to have H2 in your atmosphere, that's where you set that. You don't set that in
Yeah.
the GHG file, for example.
We should keep it for that.
Yeah.
So if you have a different run deck, let's say with the dynamic ocean, it will have more input files, it will have more source files to compile. It will be different, but the idea is that you define the big components you want at the top, you define the source files to be compiled, you define the input files, you define the parameters, and you define the years to run, and that's it. Should we go back to the presentation?
Sure, you stop sharing and I can. Right, okay.
Okay, next one.
Hit the wrong panel, sorry.
Actually, don't go to the next one.
Yes, sir.
So what we did is this, we've done everything up to the second blue line, make random, okay? And the next line shows you how to get the input data on your computer. You only do it once and that's it. After you have it set up on your computer, you don't need to communicate with our servers anymore. And then you compile the model with this command that you see, make -j setup. And that creates the whole setup of the model that you need to run later. You say after run equals the run deck name that you created in the previous command. And then you run it with the last command that you see here. .exec run e, the run ID, and then you say cold restart. And then the -np means number of processors, and we say here 2. For the M resolution, you can go up to 44. For the F resolution, you can go up to 88. In practice, you can go up to the number of latitudes of the resolution of the model, -2. And if you go above that, the model will crash. If you go below that, the model will be slow. It depends on your resource.
And consider how many cores you're running the model on. So I picked 2 here because when we originally did this tutorial, I had a laptop with 2 cores.
Yeah,
So I ran it
exactly.
with 2.
Yeah.
I did not run it with 44. It would probably not work very well.
Yeah, I mean, you'll probably run out of memory or something, but you will not gain anything. If anything, you will penalize yourself by doing that.
Right. So think about how many cores your computer has before you pick whatever NP set to.
So,
But
and
you
then,
can easily hang your laptop. Or
Oh, yes.
desktop,
yeah, you can
so-
run.
So be bigger things.
Yes.
So after running this last command, this will take like a few seconds or a few minutes, depending on the configuration. And this runs the first 2 time steps of the model, the setup hour. And then it stops, and you will have 2 forked files, 4.1 and 4.2. The 4.1 file contains the initial state of the model after reading in all the inputs, but without running anything. And 4.2 contains the model output. It's the restart file essentially after 2 time steps. And then this command exits, and you should write the same command, but without the dash called restart flag, to continue the model from the most recent file until it reaches the year E. So the model at any time that needs to restart looks for the dates into 4.1 and 4.2 and picks the most recent one and continues on that. And then when the time comes to rewrite one of the 2, it overwrites the older one. So you don't have to deal with that. It happens under the hood for you.
Just mention one more thing. One other file is written also in this cold restart that might be of interest to you. It's called the partial file, and it also includes the run ID in the name. And that is the first hour of the model,
The first time step.
the first time step, sorry, of the model that's run. And if you know, in some cases, maybe you've changed the model quite a bit, you might want to look in that partial file and see if things look okay. I think we recommend that in the tutorial setup on how to get the model going. So you can use Panoply to open that partial file up, for example, and look at your surface temperatures and see if the initial conditions you chose look like the initial conditions you expect. Because if you know your surface temperatures are all negative and you put initial conditions in that shouldn't be there, it'd be nice to know that you have made a mistake somewhere. Yeah. Okay.
And you follow the chat, right?
Yes, we're on it.
So just one slide for running with tracers. We are not going to cover it here, but there is an option to do that. This will make your model far slower depending on your choices made. In essence, we have the CBM4 gas phase chemistry for Earth, and that can be used up to for lower oxygen content in other planets or configurations. But you should not set that to 0. So you can go down to 10 to the -5 of present atmospheric levels, 6 if you want to push it, -6, I mean, but don't go beyond that. We have KBP under development for quite a while. We are getting there. And then we will be able to change the chemistry and do whatever we like. For aerosols, I mentioned OMIND matrix. This slide, yeah, we should probably remove Thomas because it's not functioning really. It's gone in future versions as well. So let's focus on OMIND matrix. It has 2 different ways to define aerosols. The OMA is saying that aerosols are fixed size and you only play with the amount. So the size of the particles is just a choice you make at the beginning. And the matrix resolves the aerosol microphysics. So you can calculate, different log normal modes, and then the total aerosol size distribution is the sum of those log normal modes. So you would use matrix if you want to simulate something that evolves quite a bit. If you don't know how it evolves, or if it does not evolve, then OMA is more than enough to use. Yeah, I don't want to go beyond that. If you want to run with tracers, please reach out with us. There are many limitations and many more configuration options to consider before even starting a simulation. So we take pride for our tracers code, but it's far too complicated to just give you instructions and tell you here you are, you can go on. So please reach out to us. We're happy to help.
And stress again, it's computationally expensive. So this is something that you want to only use in cases where you have a very good science case for using it, and you've consulted Kostas and his group about how to use this properly.
Well, just one thing I want to mention, that if you want to run Mars, run deck, I mean real Mars run deck on Planet 2, then you have to run it with tracers. And maybe I'll show you the run deck tomorrow if we have time. So that's probably the only case where basically you really need tracers to do something useful in terms of science.
Out of the templates that we have.
Yeah.
And the reason is that dust is a key component of Mars. You just cannot ignore it, and it is inhomogeneous. So a science case drives it.
Yes.
So yeah, atmospheric composition of new planets. We'll get to that, I guess, tomorrow in more detail. But remember that this model has its inheritance on Earth, so you need to decide some key Earth components whether your planet has or not. So does it have methane? Does it have ozone, meaning oxygen as well? Does it have dust aerosols? Does it have sea salt aerosols if it has an ocean? I mean, is it a saline ocean or freshwater ocean? And we never know those answers for other planets outside our solar system. So essentially, you just decide. It's as simple as that.
Depending on your science case.
Yeah, depending on your science case. And then what other aerosols you might have? I mean, are we talking about a hypothetical planet with vegetation out there? So you might have fires. So I mean, sky is the limit in your imagination when you have a science case. And of course, all these aerosols affect clouds. And moving into planet 3 into the future, the interaction between aerosols and clouds will be super sophisticated with what we have right now, but what we have right now works fine. And we should, so yeah, when you are adding in aerosols, you have to think of how aerosols will affect clouds as well when interpreting the results. Okay.
Last slide.
And then some random things that will be showing up all the time. When you do a make setup that I showed you earlier to essentially compile the model given the configuration you provide, one of the files that are created is called I, uppercase I. And this file is a transcript of the run deck itself without any things, all the things that are not related. So it contains, it does not contain, comments, they are stripped out. It only contains essentially the input files, the parameters, and the start and end date. So, and this is the file that is being read when you are starting or stopping or as you run the model. It is not the random. It is the I file that is affected. So after you do this as the setup, you can do anything you want in the random. You can delete it. And then, but the I file is the one that will be used. And if you want to make changes down the road, the most typical one being extend the simulation, it is the I file that is the simplest to modify. And I mean, there are different ways you can do things in this model. And there are sometimes preference doing this instead of that. But if you simply want to extend the simulation, the simplest way to do it is that, hey, my model went up to the nominal year 3000. I need 1,000 years more. So you go to the I file, you change the end year to 4,000, and then you restart the model as you typically do, and it will pick it up from there. And
You can also modify parameters without having to recompile the code, and they will be taken. These changes will be taken into account at runtime. So if you want to, if your end disk is to small, you can modify it without having to modify it.
Exactly, and that's one of the reasons why we have those parameters, and that's why I said so many times already without recompiling the model, because you can do that really easily. Yeah. Remember that if you modify the I file, you create an inconsistency between the run deck that you used and the I file. So what I do personally is that I might modify the run deck as well, although it's not needed, or I at least document it, because you will lose track of it and you will not remember it, and it just happens to all of us. It keeps happening. So just document what you're doing because in that respect.
Just consider, you might have done after a year 100 model runs.
Yeah.
It's hard to remember what you did on the first one.
It's impossible actually.
Yes, precisely. Yes.
The other important file is the log file. It is a file that is
Just what you mentioned about iFile. There are certain variables, I don't know, did you mention that it cannot be changed?
yes, I briefly said that yeah, you cannot change everything.
Yeah, at least DT-SRC cannot be changed during the start. It's a physics type step. So once you started your run, it should remain the same. So but dynamic time step can be changed.
TT.
DT.
Yeah, in general, the rule always applies. When you start playing with the model setup, if uncertain, reach to us. If almost certain, reaching to us is not a bad idea. So then there is this log file that is in the output directory as well, same as the I file. It is literally called log, and I think it contains nothing in it. It just exists, and it's a safety measure, so that you will not accidentally start a simulation with the same run ID while that simulation is already running, because you will start overwriting the files at random, and it's not going to look good. So what sometimes happens is that as you run the model, it crashes, and then you go in there, you figure it out, and then you want to restart it, and then the model tells you, hey, the log file is there. And the reason why it's there is because the model crashed and it had no opportunity to delete the log file. So you have to do it yourself. Yes. But when the model tells you that the log file exists, give it a second to think, am I still running this on purpose or by accident or something? It's not just a notice that says, hey, delete the log file. No, it makes you think why the log file is there, and then decide whether you have to actually delete it or something happens behind your back without realizing. The third thing is this compile with traps. So if you run the make setup, you can add at the end certain additional options, one of which is this compile with traps that you see here, that this particular one helps you debug the model. It is really important what we say in the parentheses. You have to do a make clean before compiling with traps if the last compilation was without it. And on the other side, you have to make clean if you are compiling without traps, if the previous compilations was with it. There are some hacking ways to ignore that, but we are not going there. So the idea is that, yeah, when you switch between yes and no in compile with traps, the default is no, then you must make clean. And the reason, and it is really helpful for debugging because it gives you much more comprehensive error messages when you are doing that. The reason why we don't have it always turned on is because it has a performance penalty. So you don't want to run your full model simulation with traps all the time because it will just slow you down. It's fine if you want to do it for whatever reason, but it will slow you down. And the last thing in this slide is the SSWE command. So when you're in your dex directory, you can write as you see it, /exec/SSWE and then the run ID. And this tells the model, a model that is currently running, it sends it a stop signal. So it says to the model, I don't care if the simulation is not over yet. Just go to the right place, save the fork file, and stop, because I have to do something. and that's it. So yeah, it's because you can kill it, but then it will stop at any random point, and then it will continue from the most recent fork file, but you will be missing several time steps at times. So this is a nice way to stop the model instead of just being forcing you killing it.
Yeah, because
Yeah.
if you kill it, if it's in a randomly in the process of writing
Yeah,
a restart file, yeah, that can be dangerous.
yeah, it will make a mess. And Igor has a funny story about why we chose the SSW name.
Yeah, I can tell that, but the most important thing, actually, if you kill job just by Unix kill command, sometimes you will mess up your node on supercomputer. So whenever possible, don't do this. Try to use SSWE, because like on your local computer, most likely killing it will be okay, but on supercomputer, sometimes complicated MPI jobs, they will leave some garbage and you will not be able to restart your job.
Yeah, in
Yeah,
general, I would say the only time that you should actually kill the model if it hangs, and then you're out of options.
Yeah, sometimes the model will crash, but will not actually stop running.
Yeah, and it
That
will-
sounds like an oxymoron, but it happens.
Yeah,
And then in that
one
case, you do
FBI
need to kill it.
process dies, but it does not send signal to the others that, hey, I'm dead, stop, everybody stops. So,
Yeah,
Yeah, it
on supercomputer, in that case, usually you have to basically kill
For your job.
your entire job rather than trying to fix anything inside it. Yeah, and SSW, old people in this building, not myself, but much older people remember what it was. Actually, it's the meaning is some switch. That's something either some button or some switch which existed on some very old Sun computer, which basically when you turn it on, it would change certain bit in certain register from 0 to 1, and people could see it from the program or that this bit has changed. So please stop the model. So that's left for this historical reason.
Well, the same name as run deck.
Yeah, the same for run deck. It just means deck of punch cards which controls your own.
it's an old model.
It's a legacy
Yeah.
model.
That's for when computer was so big that bugs were actual bugs in the computer.
In the computer. Yes.
That's where the word
Yeah.
bug
I didn't
stands.
know that. Oh, wow.
Get in the computer. They get fried on a logic board.
I've seen that with mice and out in the field campaigns.
Mhm.
Oh, I've seen it in my office.
Okay,
Back in
okay,
Austria.
Too much information.
okay. We're going to take you want to have a question? Yeah?
What information do you get from the extra flags?
So the extra flags, the -00 turns off the optimizations completely. And I never seen that affecting anything in terms of the debugging. It makes the compilation faster because you don't optimize, but I don't use it anymore.
It definitely helps with debugging because especially if you want to run the model in debugger and sometimes just print out if the model crashes. With O0, basically compiler doesn't change doing anything funny to your code. It just compiles as it is. So all variables are available because it doesn't optimize them out. And order of execution exactly the same as it is in your model. So sometimes you get much more useful output because like this high optimization is often like printout will be completely cryptic. Variable names will not be mentioned and some function calls could be skipped. So yes, I definitely would use O0.
But it gives you the variable name and the line number in the file where
That's
there's an
it.
issue.
Different flags do that. The -00 just removes optimization, and it's usually when you run a debugger.
Yeah,
But in my case, that I never ran a debugger, the 00 never really gave me something additional.
So if I, sometimes I get those lines where it's just asterisks where I might be getting the line of the code where the
Yeah.
problem is.
Yep.
Would that help?
No.
Yep. Yeah.
Yeah.
No.
this I still
There
have
will
to
always be a few lines that are cryptic, and then the actual line that you care about.
Yeah. Okay.
So the lines above, you don't care. And I
And
mean,
sometimes,
for
you know,
most
like, sometimes
cases, yeah.
it's, you can't tell what's actually causing the model. to
You may
crash.
mention some example.
So if everything is cryptic, you have not done make clean.
No, not everything. It's sometimes, you know, there's a problem somewhere in the code and the errors are not helpful. From the.
Yeah, sometimes it happens.
Yeah.
Sometimes it happens. The O0 never helped me on that. Changing compiler sometimes helps.
Yeah, it depends on compiler. I mean, that's, I guess, different topic for discussion,
Yeah.
what happens.
And the -G is just enables some debugger optimizations, debugger flags as well, right?
It adds debugger information to the code. It's also debatable. Some people say that you should always use it because it never hurts, but in old days, actually, it would slow you down sometimes, and sometimes it would change optimization level. So we don't include it at least into optimized code that we use for running the model.
Okay, we're going to take
Actually,
a break
One
here.
thing I
Yes.
think I wanted to mention, it looks like there was still some confusion on the chat. So we probably should stress again that basically what are our years in the run deck. So at the end of the run deck, the years you specify start year and end year. Those are basically just indices to label your output from the model. They don't have effect. Well, in most cases, it don't have effect. Master year that you specify, it's basically, it specifies the year for four things that you specify in your files. So it's also makes sense. I mean, you have to specify it, but it makes difference only if you have files with real forcings. You nearly always have this the greenhouse gases file, and sometimes you would have like a lot of other files. But keep in mind that basically those are sort of like decoupled things. But you have to, you may set a master year equal to 0. Then those years at the end of the run deck, which you specify, they will be used as basically lookup years to look for your forcings in the forcings files for greenhouse gas. But for most planetary runs, those are kind of decoupled, so you can just choose start year and stop year just to make it more convenient for your output. So for non-Earth runs, you should use like year 1 to start and then year end to how many years we want to run.
Okay, we're a few minutes over our planned break, so we're going to stop it here and we will reconvene in an hour and 5 minutes. And if you have questions in the meantime, you can put those in the chat and we can try to address them when we return. I will stop.